In this video, we will discuss Einstein's general relativity theory, and this is the theory that brings rise to the modern astrophysics and cosmology we know today. This is the theory that started everything off. So the idea behind general relativity, since special relativity from 1905 considered constant speeds, general relativity from 1915 considered changing speeds, so that's a constant acceleration. And the only natural constant acceleration that we all endure, that is gravitational free fall. And so it was Einstein who connected free fall to weightless floating, which allowed general relativity to become a modern theory of gravity. And I must warn you, the mathematics leading up to it may be a bit difficult, but it's all notation purposes, and I'll walk you through it. But despite the complexities of this mathematics, we hope to understand what general relativity is all about and why it's considered as Einstein's masterpiece, and how it helps us in understanding astrophysics, cosmology, and everything involving space. By 1907, Albert Einstein wanted to incorporate acceleration to his 1905 special theory relativity, and it puzzled him how to incorporate acceleration to a theory that's strongly based on constant speeds. But then he thought, what would happen to you inside an elevator when it's moving up versus moving down? So if you have the suspension cord of the elevator cabin, if that were to be cut, then you and the elevator cabin would be in free fall. And since you have no idea what the outside world looks like, you are within this enclosing. Then what you would experience as gravitational free fall would just be weightless floating, and that free fall is really drifting across space over time. But if the elevator were rising, if it's moving up, then the acceleration of the frame would simulate stronger gravity. So because of relativistic acceleration, Albert Einstein can connect that to gravitational free fall. And that is his beginning phase for general relativity. Just as how Isaac Newton connected the falling apple to gravitational free fall, Einstein connected free fall to weightless floating. And a consequence of that idea, consider you have a light ray that's being shown in the cabin, seen by an inside observer and seen by an outside observer. For a person inside the cabin, while it's free falling across time, the light beam would just be a straight beam from wall to wall. But according to an outside observer, while the cabin's in free fall, although at every singular moment of time the light beam would be straight, but in the overall case, the incident light beam would be a curved beam over time. So it is this idea that gravity bends light, and to keep the speed of light constant, special relativity was all about length contraction and time dilation. And so if gravity can bend light, gravity can also bend space and time. Length and contraction are curvable simultaneously and instantaneously. And with that, I do want to introduce some mathematics. Space-time, because they curve simultaneously and instantaneously, Einstein needed to combine the 3D space and time as a singular entity of four-dimensional space-time. Now, 4 dimensions might be hard to conceptualize, but let's put it in this way. We take 3D space with our x, y, and z coordinates, and we consider that the dot product between two different dimensions, an x, y, y, z, or z, x, their dot product is equal to 0 because they're perfectly perpendicular. If you have a dot product of two of the same dimensions, so an x, x, y, y, in ZZ, you get a dot product of 1. But try putting time into that mix. How would you align time with any of these spatial dimensions? If it's parallel, then you have a dot product of 1. If it's perpendicular, then you have a dot product of 0. Let's also consider anti-parallel, which means that time is pointing in the opposite direction as one of the dimensions. That makes a dot product of -1. So is the dot product between space and time 1, 0, or -1? Well, because that they depend on each other, it can't be 0. So it's either the +1 or the -1. And there are two different ways to combine space and time based on the fact that their dot products are either 1 or -1. And let's consider the fact that of two different ways of adding adding time to space. And let's put it into this displacement vector. Space and time are perfectly parallel, so they're +1. You get time as positive and r as positive, and r is our space. And we could write this in this format. And we have a Greek letter here. Greek letters are just notation purposes. But as we see Latin letters that resemble 3D space, Greek letters of mu nu or alpha beta or anything in the Greek alphabet, they are a set of 4 dimensions. So you have ct, c being the speed of light and t being time, so they form some space dimension. You have x, y, and z. If you have anti-parallel, so you have time and space to be a -1 dot product, then time here is the one that's negative, and time is left positive. And in the notation purposes here is that our Greek letter is in the subscript. Before, when it's a +1, it's a superscript. It's all notation, so don't be confused by notation. It's just a way of writing it. But if you convert one to the other, so if you take a number and you multiply that by -1, you turn that positive number into a negative number. You do it again with another -1 and you turn a negative to a positive. So by multiplying a negative to either number, you can convert one into another. So similarly, when you do that with these type of vectors with subscripts and superscripts, you can introduce this beast. And this beast, well, good news is that these two variations are quite equal to each other. But this thing is called the metric tensor. Now, tensors, it may be the first time you're hearing the word, and fear not. We have scalars and vectors. Scalar is just a numerical value with units. We have a vector that is magnitude and direction. Now, tensor, it just adds another component to it. It does have a magnitude, it does have a direction, but it has another characteristic which I call stress. Stress as in that each of the components of a tensor is independently changing and it is able to be changed. And as I mentioned here, tensors, yes, they may sound scary and they are complicated and they do require extra attention on their own. But sadly, they are important to general relativity. But to put lipstick on a pig, tensors, they're very large vectors with more components than we actually care for. And to avoid any of the lengthy and scary detours of learning tensors, let's just get familiar with the most important ones. We saw this already. And this metric tensor, it just tells us how flat our landscape of space-time is. And when you go hiking in the mountains, you don't see that the landscape is flat. You see the mountains, you see the valleys, you see the rivers, you see the cliffs. So the landscape is hardly ever flat. It's also curved and it's also bumpy. And what makes this landscape of space-time curved and bumpy? It is this tensor, and it's called the Ricci curvature tensor. And since we're introducing gravity as a general relativity part, then we need to consider the fact that these curvatures of space-time must be induced by a source mass, by a source rest energy. And that is in tensor form of the energy stress tensor. So with these three tensors, we can go ahead and approach general relativity, hopefully with an open mind and a fearless heart. Curving space-time. It may sound difficult conceptually, but it's not really that hard to think about. You can think of curving space-time as looking at the Earth landscape. Here in our little neck of the woods in Greenville, we see that the entire landscape is flat, with the occasional hill, of course, but normally it's flat, and that's why we have flat earthers. They assume the Earth is flat because all they see is a flat landscape. But what we see as flat is just a small segment of an entire curved entity that an astronaut would see from the ISS. So curving space-time is as going from flat landscape to a curved landscape. And this is just based on perception, and it's based on what we see relative to us. So we draw an arrow on our flat grid and how it will look on a curved surface. That flat arrow, that's straight, would look bent along a curved surface. So on a flat landscape, when we look at this arrow, at this hypotenuse, we consider our 4 dimensions of time here first, and we have our 3 dimensions of space, x, y, and z. And this is all in the Cartesian coordinates. For an astronaut looking at the whole curved surface, the Cartesian coordinates become spherical coordinates, and that time is left alone, but x, y, and z is compressed into r, and we introduce angle dependency with our d theta and our sine theta d phi. So the top equation is for a local perspective, and the spherical one is for a global perspective. But suppose that we have an astronaut that's free falling towards the Earth. So the perspective here would go from global to local, meaning that we're going to go to a curved surface and we're going to zoom in into a flat surface. So curved and flat are 2 different perspectives. So that means we take this and these individual ds squared coordinates, and we introduce 2 Greek letters called the before and after case. Alpha is before, which is what we start off with at the global view, and beta is our after when we look at the flat. And this is all considering instantaneous free fall, changing our perspective from curved to flat. So when we go ahead and label this, it's all notation purposes, all the alphas and betas. So don't be scared about how it looks aesthetically. Here is our tensor, our metric tensor, our pre-existing space-time, and we have 2 vectors that look rather weird. They both have a mu nu, and mu nu, they're the pre-existing coordinates, and alpha beta are the instantaneous before and after coordinates. So just as we have a curved arrow, which is the same as a flat arrow, seeing a curved arrow that's pre-existing turn into a flat arrow, that is changing the shape of that arrow that is pre-existing. So that's how we introduce these 2 vectors, as although pre-existing, they're also changing based on the perspective of the free-falling astronaut. So while in free fall for an astronaut, the perspective of the Earth goes from curved to flat. In terms of the actual fabric of space-time, supposing that the astronaut begins at the very edge of gravitational attraction, he starts off at the flat landscape, and when he's falling in, he's going along the curves made by the planet. So the perspective of the landscape goes from flat to curved. And so since we have a changing perspective, then that means we have a changing metric. So that means we could go, all notation purposes, mind you, we go from the mu nu pre-existing space-time to instantaneous, based on perspective, alpha beta notation. And do note that our changing metric is based on pre-existing curvature. So when we introduce the Ritchie's curvature scalar, we have this r with the mu nu, and mu nu is pre-existing coordinates. 1/2, that's just a number. Here is our changing metric based on perspective, and we have gradients. And what they show us is that it will change over time and space based on pre-existing curvature, but also based on our perspective. And that's how we have the alpha, beta, mu, nu notation for our two gradients. So this is only considering half of the curvature. Because we have a spherical object, we need to consider the spherical dissymmetry of our planet. And it's really, total curvature is just as easy as multiplying this by 2, and that's how we get this. But as a proper definition, you have a Ritchie curvature, and you have the metric tensor here. And this is all of them together. This is called the Einstein tensor here. And this number here, that's just the Ritchie scalar, and that is a numerical value of the actual depth of curvature. And so we can able to describe source curvature or pre-existing curvature by an astronomical source. And so we can do that by considering gravitational flux. So just as I talked about Gauss's law of electric fields as compressions of the electric field, and if you squeeze down that field, you get the source charge density. For gravitational flux, you squeeze down that gravitational field, and what you get is the source mass density. And so we could go ahead and go through the motions of the math. And the method is practically the same as Gauss's law, and that we're able to see that the source of gravitational fields are indeed astronomical mass densities. And so, since the gravitational field is a conservative field, it has a potential, and it can be described as a minus gradient. And we could turn Gauss's law into an equation that looks similar to total curvature, which is this. Now, to think about space-time and the gravitational potential field, when we see these warpings of these curvatures of space-time made by an astronomical object, we are actually looking at the space-time as a gravitational potential field that any dips and curves of this field tells us the strength of gravity. And this is exactly how I describe the potential, the electric potential in terms of the electric field, and that if we have a landscape of the potential, the sharpness of the dips and of the curves tells us the strength of the field. This is exactly what's going on in a more gravitational sense. So we have a rest energy belonging to a mass and weighs in on the landscape, curving the space-time into a gravitational well. And at the center of this well is a rest energy density. And since everything is based on tensors, there is a tensor equivalent to this rest energy density, and that is the energy stress tensor, which is the T mu nu here. And this form, this comes from the Gauss's law up here. It's just turning the minus gradient squared into the Ritchie curvature. And that is practically what these curvatures are. They're these changes of the gravitational potential field. And these changes of the field are induced by Ritchie curvatures. Total curvature is just as simple as multiplying everything by 2. And once you get the G mu nu, the capital G mu nu, and times this by 2, and you get this side of the equation. And lo and behold, this is indeed Einstein's equations for general relativity, which are presented right here. So what this is telling us is that we know what gravity is. When gravity was discovered by Newton, he was able to describe it as an interaction, but yet he did not know what gravity was in the purest form. Einstein, however, told us that gravity is just these geometrical warpings upon the space-time landscape, and the deepness of these curvatures is the strength of the source gravity. And what we experience as free falling, just as the astronaut begins to free fall, he is just curving or gliding along the curves of the landscape fabric.